the picture of a perfect fit is something like I have two leaves, they don't meet, this is somehow like over at infinity of my plane, but if I take nearby ones, they absolutely do. Okay. This could be the end of my plane, or maybe I could see branching leaves that either of these is permitted. So. Okay, here's a proposition that I always think is a great warm-up as you start to deal with these objects, and to say, how does the presence of an Anosov-like action constrain what these foliations look like? So let me, in case I run out of space, let's just start on this board. I never know how much space things take. So proposition, our first little warm-up of how Anosov-like constrains foliations. Suppose that I have two leaves that make a perfect fit. And I have an Anosov-like action, and one of these leaves is fixed by a non-trivial element of G. Let's say L plus. G is not the identity. All right, well then, some things I'm gonna get for free. So let me write this part for free, and we'll remember we don't have to prove it. Point one says that there exists a fixed point for G on L plus, okay? So I'm gonna name this X, okay? Something we do have to prove is that I claim that G also fixes the leaf, L minus. And so, of course, property one also tells me that there's some fixed point, I don't know why, of G on L minus. All right, that's an axiom. And so encoding this in a picture, I have my L plus, I have my perfect fit with L minus, I have some point fixed by G. I mean, the dynamics are like this, up to switching with the inverse. I have another point here, which is fixed by G, a unique fixed point. And I can look at the other leaves through these two fixed points. Right? And the conclusion is, this pair also makes a perfect fit. Right? So that's what this proposition is really about. And so let's see, that's the minus foliation leaf through X, and the plus foliation leaf through Y, these two, these also make a perfect fit. So a perfect fit plus a fixed point gives me another one. Okay. Let's prove this. Half of it is already done. So I have L plus, I have my point X, and I need to show next that this leaf L minus is fixed. I'll keep the statement. So far I just have this type of dynamics. So definition of perfect fit says that if I take leaf, so let's forget L minus for the second, and let's look at some leaf, oh no, I need another levator, I don't know, little f or something for phi, that passes through that passes through this leaf L plus on the side of the fixed point where L minus lives. Right? This leaf cuts the plane in half, takes something on the half where I was seeing L minus. Right? If I iterate f under G, the power that's expansive in this direction, I'll get a sequence of leaves that accumulates to something. It doesn't go off to infinity because L minus is preventing me from leaving every compact set. This will accumulate to either a leaf or a union of leaves that includes L minus. So to write this, G to the N of F is a sequence of leaves, and this limits to a leaf, or if this leaf was at a non-Hausdorff branching point, or union of leaves in as a sequence that converges to something in the leaf space of L minus, sorry, F minus. Okay. All right, so what could happen a priori is that there's some big sequence like this that it accumulates onto. Okay. But I already know that there is a leaf here that makes a perfect fit. Here I'm gonna, to not be completely pedantic, I'm going to be slightly sloppy and ask you to fill in the details. I claim that the perfect fitting leaf, because it has the property that neighborhoods of leaves that pass through it limit on, sorry, leaves that pass through it limit on to L plus. The other direction of every neighborhood of L plus in the leaf space contains something that intersects it. L minus has to actually be a closest leaf. I couldn't have had something like L minus down here and then some other leaves in the limit in between. Right? If not, this will break the property of perfect fit where every neighborhood of this one contains leaves that go through L minus. Okay? So in fact, L minus is, if not the unique leaf, it is the one closest in some, take a transversal that passes through all of these copies, the one closest to L. Okay. So L minus making perfect fit implies that, well, I guess what I should have said a minute ago is that this limit collection as a collection is always going to be unvariant under G. It's a limiting object of the dynamics of G. And what I need to worry about is if there were many things in it beside L minus and if they were non-trivially permuted. But the fact that L minus is closest to this invariant leaf by G tells me that it must be itself invariant. So this is in the limit and itself fixed by G. Okay, so this is an accurate drawing now of L minus here at the edge of this picture. Okay, so already for free here, now I have a fixed point coming from axiom 1. I think I'm only ever gonna use axiom 1 in this entire proof, not the other ones. So here's Y, and I look at the leaf through it. So I can erase some of this extra scratch work from my picture. F is not needed anymore. That was just to get me the proof that I wanted. Here's L minus, I have Y, a fixed point for the action of G, and I have a leaf through it. So my next assertion, well, they make I'm supposed to show it makes a perfect fit with this red leaf through X. All right. Okay, so there's two things to check. One is that they don't intersect. If these two leaves did intersect, well, this leaf is invariant by G. This leaf is invariant by G. Y have transverse foliations. They can meet at most one point, so that point has to be fixed by G. This is bad because G is supposed to have globally expansive or contracting dynamics, so this point is supposed to move under iteration, not be fixed. Okay. So axiom property 1 in the definition again implies that, what was I calling this? The minus leaf through X and the plus leaf through Y don't intersect. Is the empty set. So this cannot happen. Now we have an extra fixed point. I have a unique fixed point in each leaf. All right, and now I need this neighborhoods property again. And this I get, again, by iterating the dynamics. So for instance, to check that this leaf is accumulated on by leaves that meet this one, the plus one. Well, here, how about I take in a different color, so my drawing doesn't get too bad, some leaf here. Here's a new f, let's call it f prime. And I can iterate it under G inverse. As I iterate, it's going to approach x. So that means as a leaf, it approaches this red leaf in the leaf space. Right. G to the minus big N of f prime. But of course, it's at the beginning, it intersects this G invariant leaf. So at all times, it intersects this G invariant leaf, the one I awkwardly called f plus of y. So it's also at all times intersects f plus of y, which is half the definition of making a perfect fit. This leaf is accumulated on by ones that intersect f plus of y. And my picture is completely symmetric, so it works in the other direction too. All right, so here's the picture for why they make a perfect fit. Half of it, and then symmetry is the other half. Okay. I like to do this argument because that's the kind of chasing around that you do to prove many of the other statements that I'm now going to assert but not prove. If you can do this backwards and forwards with your eyes closed as a warm-up, and you have a lot of time and willpower, you can prove the other things that I will state.